Welcome! In this session, we'll explore LeetCode problem number 1832, check if the sentence is Pangram. This interesting problem challenges us to verify if a given sentence contains all 26 lowercase English alphabet letters. Stay tuned as we break down the solution step by step. To solve this problem, we need to understand what a pangram is. A pangram is a sentence that includes every single letter of the English alphabet at least once. For example, if you're given a string called sentence, which only contains lowercase English letters, your goal is to determine whether it's a pangram or not. If it is, you return true; if not, you return false. The input is always a string that's at least 1 character long and at most 10,000 characters. The output is a simple Boolean value, true if the string is a pangram, and false if it's not. Let's look at the first example. The input string is "The quick brown fox jumps over the lazy dog." When we examine this sentence, we see that it contains every single letter of the English alphabet, from A to Z, at least once. Because no letters are missing, this sentence qualifies as a pangram. The output is true in this case. Now, consider the second example. If the input string is LeetCode, you'll notice that it doesn't include all the letters of the alphabet. For instance, letters like B and F are missing, so this string is not a pangram. Here, the output is false. To break it down further, in the second example, we can see that several letters are completely absent from the input. For instance, letters like B, C, and F are not found anywhere in the string LeetCode, which is why it doesn't meet the criteria of a pangram. On the other hand, in the third example, the input is the string ABCDEFGHIJKLMNOPQRSTUVWXYZ. This string explicitly contains all 26 letters of the English alphabet, from A to Z, in order. Since no letters are missing, this example is a valid pangram, and the output is true. This illustrates how the presence of all 26 unique letters is the key requirement for determining a pangram. Finally, let's consider the constraints and edge cases. The string sentence is guaranteed to only have lowercase letters, so there's no need to worry about uppercase letters or special characters. For edge cases, a string with a length of just 1, like A, cannot possibly be a pangram because it's too short to include all 26 letters. The shortest valid pangram would be a string that contains exactly 26 unique letters, like ABCDEFGHIJKLMNOPQRSTUVWXYZ. Additionally, repeating letters in a string, such as AABB, don't make it a pangram unless all 26 letters are included. Even strings longer than 26 characters aren't guaranteed to be pangrams unless they explicitly meet the requirement of containing every letter at least once. To solve the problem of determining if a given sentence is a pangram, we considered multiple approaches. The first approach is the brute force method, where we explicitly check for the presence of every letter in the alphabet within the sentence. The idea is simple: maintain a complete list or set of all 26 lowercase English letters, and for each letter, verify whether it exists in the sentence. If we find all 26 letters, we can confirm the sentence is a pangram. While this method ensures correctness, it involves iterating through the entire alphabet and scanning the sentence repeatedly, which leads to redundant checks and inefficiencies. Although its time complexity is technically O(n), since the alphabet size is constant, it doesn't leverage any optimizations to reduce unnecessary operations, making it less ideal for larger inputs. An improved solution is to use an optimized approach based on sets. Instead of checking each letter individually, we can leverage a set's ability to track unique elements. By iterating through the sentence, we add each lowercase letter to the set. The moment the set contains all 26 letters, we know the sentence is a pangram and can terminate early. This method eliminates redundancy by focusing only on distinct letters, and the use of a set ensures that each character is processed just once. The time complexity remains O(n), because we perform a single scan through the sentence, and the space complexity is effectively O(1), as the maximum size of the set is capped at 26. This approach is both efficient and easy to implement, making it a strong candidate for solving the problem. Another approach we considered involves using bit masking to track the presence of each letter. Here, we use a 26-bit integer where each bit corresponds to a letter of the alphabet. As we iterate through the sentence, we calculate the relative position of each character and update the appropriate bit in the integer. If all 26 bits are set to 1 by the end of the process, the sentence is confirmed as a pangram. This method is highly space efficient, as it requires only a single integer to store all the information. Its time complexity is O(n), similar to the set-based approach. However, bit masking introduces additional complexity in terms of implementation and readability, which may not be justified given the problem's simplicity. While it's an interesting solution, it is less practical for this specific case. Among the approaches considered, we selected the optimized set-based solution as our strategy. This approach strikes the perfect balance between simplicity and efficiency, making it easy to implement while also minimizing redundant computations. The brute force method, although straightforward, is less efficient due to its repeated checks for each letter. On the other hand, the bit masking approach, while space optimal, adds unnecessary complexity that isn't needed for a problem of this scale. The set-based solution provides O(n) time complexity and O(1) space complexity, and its intuitive nature ensures clarity and maintainability. The key insight was recognizing that tracking distinct letters directly using a set eliminates redundant checks, and the fixed size of the alphabet allows us to terminate early once all letters are found. These factors make the set-based solution the most balanced and effective choice for solving this problem. In this problem, we are tasked with determining whether a given string, called sentence, is a pangram. A pangram is a string that contains all 26 lowercase English letters at least once. For example, the sentence "That brown fox jumps over the lazy dog" is a pangram, as it includes every letter from A to Z. To solve this problem efficiently, we can utilize a set-based approach. The key idea here is that sets automatically store only unique elements, so we can use this property to track which letters from the alphabet appear in the string. First, we clearly define the scope of the problem. Since the alphabet has 26 letters, our goal is to ensure that the string contains these 26 unique letters. As an initial optimization, we can immediately return false if the string length is less than 26, as it's impossible for it to be a pangram. Next, we initialize a set to store the unique letters we encounter in the string. This is particularly useful, as sets automatically handle duplicates and allow us to efficiently check whether we have all 26 letters by comparing the size of the set to 26. To populate the set, we iterate through each character in the string and add it to the set. Since sets store only unique elements, adding duplicate letters will not increase the size of the set. Once we've processed all the characters in the string, we check whether the size of the set is exactly 26. If it is, we return true, as this means the string contains all 26 letters. Otherwise, we return false. There are a few key insights that make this approach efficient. First, the use of a set simplifies the problem significantly, as we don't need to explicitly track or count the frequency of each letter. Once a letter is added to the set, duplicates are ignored automatically. Second, we can optimize further by including an early exit condition. If the string length is less than 26, we know it cannot possibly contain all 26 letters, so we can return false immediately. Finally, this approach ensures optimal iteration through the string, achieving a time complexity of O(n), where n is the length of the string, as we process each character only once. The set also has an average constant time complexity for insertions and checks, and its space usage is minimal, as it can only grow to contain up to 26 elements. Now let's delve into the detailed steps of the algorithm. First, we validate the input by checking whether the string length is less than 26. If it is, we return false right away. Next, we initialize an empty set, which will be used to store the unique letters we encounter. Then, we iterate through the string, character by character. For each character, we add it to the set. Since sets automatically ignore duplicates, we do not need to handle repeated characters manually. Additionally, we can include an early exit condition within the loop. As soon as the set contains all 26 letters, we can return true immediately, without needing to process the rest of the string. After the loop, if the set size is still less than 26, we return false, as not all letters are present. If the size is exactly 26, we return true. To implement this algorithm in Python, we start by checking the string length. If it's less than 26, we return false. Otherwise, we create an empty set called unique_letters. Then we iterate through the string, adding each character to the set as we go. If the set size reaches 26 during the iteration, we return true. Finally, after completing the loop, we perform one last check to determine whether the set size is exactly 26. If it is, we return true, as this means the string is a pangram. Otherwise, we return false. This approach also accounts for edge cases. For example, if the input string is empty, we return false, as it contains no letters. Similarly, if the string is shorter than 26 characters, it cannot be a pangram, so we return false. Strings with duplicate letters will still yield the correct result, as duplicates are ignored by the set. Additionally, the early exit condition ensures that we can stop processing as soon as all 26 letters are encountered, making the algorithm faster in cases where the string is already a complete pangram. In terms of complexity, the algorithm is very efficient. The time complexity is O(n), where n is the length of the string, as we process each character only once in set operations like adding elements and checking the size are O(1) on average. The space complexity is O(1), because the set size is capped at 26, regardless of the string length. This makes the solution both time efficient and space efficient. Let's go through a couple of examples to see the algorithm in action. First, consider the input Feckwick brown fox jumps over the lazy dog. We initialize an empty set called unique_letters. As we iterate through the string, each letter is added to the set. By the time we finish processing the string, the set contains all 26 letters of the alphabet. We check the size of the set, which is 26, and return true, indicating that this string is a pangram. Now, take the input LeetCode. Again, we initialize an empty set and add each character to it as we iterate through the string. However, by the end of the iteration, the set contains only a few unique letters, and its size is less than 26. Therefore, we return false, as this string is not a pangram. These examples demonstrate how the algorithm efficiently handles different cases, ensuring correctness and optimal performance. By leveraging the properties of sets, we can solve this problem in a concise and effective manner, covering all possible scenarios. This solution to LeetCode problem number 1832, check if the sentence is pangram, is both concise and efficient. We begin by defining the function checkIfPangram within the solution class. The function takes a single parameter, sentence, which is the input string we need to evaluate. To determine if the sentence is a pangram, we use a set to collect all unique characters in the string. A set is ideal here because it automatically handles duplicates and keeps only unique elements. The line unique_chars equals set, sentence, creates this set. Next, we check whether the number of unique characters in the set is exactly 26, which corresponds to all the letters in the English alphabet. This is done with the simple condition len, unique_chars equals 26. If the condition is true, the function returns true, indicating that the sentence is a pangram. Otherwise, it returns false. This approach is highly efficient, with a time complexity of O(n), where n is the length of the input string. The space complexity is O(1), since the set size is limited to at most 26 unique letters. This solution handles all valid inputs gracefully, as the problem guarantees that only lowercase English letters are present in the input string. Overall, the implementation is clean, leveraging Python's set data structure for optimal performance and readability. This is the Java implementation of the check if the sentence is pangram problem from LeetCode. The logic mirrors the Python implementation and uses a hash set to collect unique characters from the input string. Since Java requires explicit type declarations, we use asSetCharacter to store the unique characters. The solution then checks if the set size equals 26, indicating that the sentence contains every letter of the English alphabet. This approach is efficient and concise, leveraging Java's built-in collections. In this problem, we are tasked with determining if a given sentence is a pangram. A pangram is a sentence that includes every single letter of the English alphabet at least once. To solve this, the provided solution uses Python's set data structure, which is particularly useful because it automatically stores only unique elements. Let's break down the code. First, we define a class solution with a method checkIfPangram that accepts a sentence as input. The key idea here is to convert the sentence into a set of unique characters using set_sentence. This allows us to extract all distinct letters in the sentence, ignoring duplicates. Next, we simply check if the size of this set equals 26, which is the total number of letters in the English alphabet. If it does, the sentence is a pangram, and the function returns true. Otherwise, it returns false. For example, consider the input sentence equals "that quick brown fox jumps over the lazy dog." First, we convert this sentence into a set of unique characters by calling set "that quick brown fox jumps over the lazy dog." Here, the result of converting the sentence into a set gives us unique _chars equals U, Q, I, E, L, Y, W, D, O, A, J, Z, C, T, V, H, X, B, M, G, P, R, F, N, K, S. This set contains all 26 letters of the English alphabet, which is exactly what we're looking for. The next step is to check the size of this set using len, unique _chars equals 26. Since the size is indeed 26, the condition evaluates to true, and the function returns true, indicating that the sentence is a pangram. Now, for another example, let's test the input sentence equals LeetCode. After converting this sentence into a set, we get unique _chars equals E, D, T, O, L, C. This set contains only 6 unique letters, which is far fewer than the required 26. When we check len, unique _chars equals 26, the condition evaluates to false, so the function returns false. This tells us that the sentence is not a pangram. The result of the second example confirms that the sentence LeetCode is not a pangram, as the function returns false. Let's now look at another example. For the input sentence equals ABCDFGHIJKLMNOPQRSTUVWXYZ, we convert the sentence into a set of unique characters using set ABCDFGHIJKLMNOPQRSTUVWXYZ. The result is unique _chars equals U, Q, I, E, L, Y, W, D, O, A, J, Z, C, T, V, H, X, B, M, G, P, R, F, N, K, S. As you can see, this set contains all 26 letters of the English alphabet. When we check the size of the set using len, unique _chars equals 26, the condition evaluates to true, and the function returns true. This confirms that the sentence is indeed a pangram. These examples demonstrate how the method leverages the properties of sets to efficiently solve the problem by focusing on uniqueness and size. The key insight behind this solution is the use of Python's set data structure, which automatically removes duplicate characters and retains only unique ones. For instance, when we process the sentence LeetCode, the duplicate E is removed in the set, leaving us with unique _chars equals E, D, T, O, L, C. By checking the size of the set against 26, we can determine if the sentence includes every letter of the alphabet. Summarizing the intermediate results, in example 1, the size of the set is 26, so the function returns true. In example 2, the size is only 6, so the function returns false. Finally, in example 3, the size is again 26, so the function returns true. This approach ensures a clean and efficient way to check if a sentence is a pangram by focusing solely on the uniqueness of characters and their total count. To analyze the time complexity of the solution, we start with the process of creating a set from the input string sentence. This involves iterating through each character in the string, and since each insertion into the set operates in constant time on average, the overall complexity of this step is O(n), where n represents the length of the string. Next, we perform a length check on the set to see if it contains 26 unique characters. Calculating the length of a set is a direct operation with a time complexity of O(1), as is comparing the result to the constant value 26. Since the set creation step dominates, the total time complexity of the solution is O(n). This holds true across best, average, and worst cases, as the entire string must always be scanned to build the set regardless of the outcome. Now, let's consider the space complexity. The main contributor to the space usage is the set unique _chars, which stores up to 26 unique letters of the English alphabet. Even in the worst case, where all 26 letters are present, this is constant space, O(1), because the maximum size of the set is fixed. However, during the iteration over the string, the set temporarily grows as characters are added. In the worst case, it may store up to n 26 characters, where n is the length of the input string. Additionally, the input string sentence itself requires O(n) space to store in memory. Combining these factors, the total space complexity is O(n), with the input size being the dominant factor and the set contributing only a constant amount of additional space. Let's compare this approach to a more naive solution. A brute force method might involve iterating over each letter of the alphabet and checking if it exists in the string sentence. This would require traversing the string 26 times, resulting in a time complexity of O(26*n), which simplifies to O(n). The space complexity would remain O(n), as the input string still needs to be stored. By contrast, the optimized approach uses a set to record unique characters in a single pass through the string. This eliminates redundant checks and ensures the time complexity is O(n). Space complexity remains O(n), dominated by the input storage. Finally, from a mathematical perspective, the set operations are efficient, with each insertion taking O(1) on average. The length check and comparison operations are constant time, so the overall time complexity of O(n) and space complexity of O(n) hold true for this optimized solution. When solving this problem, there are several common mistakes to watch out for. One of the most frequent issues is not accounting for the problem's constraints, such as case sensitivity. Since the input will only contain lowercase letters, any conversion of uppercase letters or handling of non-alphabetic characters is unnecessary and wastes computational resources. Another pitfall is incorrectly handling duplicate letters. For this task, we only care about the presence of each letter, not how many times it appears, so counting frequencies adds unnecessary overhead. Using inefficient data structures is another common mistake. For example, using a list to track seen letters and checking membership with the IN operator results in slower performance due to linear lookups. A set is a much better choice here, as it provides constant time average lookups. Additionally, some solutions fail to terminate early once all 26 letters have been found, leading to wasted processing time. Finally, overcomplicating the logic, such as manually mapping letters to indices or using ASCII values unnecessarily, can introduce bugs and make the solution harder to follow. A straightforward approach with sets or direct comparisons is more effective and less prone to errors. This problem is often used in interviews to test your understanding of hash-based data structures like sets. It's a great opportunity to demonstrate how efficiently sets handle membership checks and how you can identify edge cases, such as empty strings or strings shorter than 26 characters. Once you've presented your initial solution, discussing potential optimizations can help you stand out. For example, you might explain how early exiting as soon as the set size reaches 26 minimizes unnecessary processing, or how avoiding redundant checks improves runtime. Additionally, be prepared to discuss space complexity trade-offs. While using a set requires O(n) space, you could alternatively leverage bit manipulation, which reduces space usage to O(1). However, bit manipulation, while efficient, can make the code harder to read and debug, so it's important to weigh these trade-offs and communicate them effectively during the interview. This problem also connects to several related LeetCode problems that help deepen your understanding of string processing and hash-based approaches. For instance, in LeetCode 242, Valid Anagram, you work on verifying character frequencies, typically using hash maps or arrays. LeetCode 49, Group Anagrams, takes this concept further by grouping strings based on their character counts, showcasing more advanced hash map usage. LeetCode 266, Palindrome Permutation, tests your ability to determine if a string can be rearranged into a palindrome, often using hash sets to track character occurrences. Finally, LeetCode 423, Reconstruct Original Digits from English, challenges you to process strings to identify all digits, which involves applying similar frequency-based logic. Exploring these problems can help you build a broader skill set and better understand how to adapt hash-based techniques to different scenarios. Now let's explore some alternative approaches to solving this problem. The most optimal method is using a set to track the letters you've seen. By adding each letter to the set and checking its size, you can determine if all 26 letters are present. This approach has a time complexity of O(n) and a space complexity of O(1) if you consider the set size fixed at 26. Another approach is bit manipulation, where you use a 32-bit integer to represent the presence of each letter with individual bits. When all 26 bits are set, you know the string is a pangram. This method is space efficient, using only O(1) space, but it can be harder to implement and debug. A simpler alternative for beginners is a frequency array, where you use a Boolean array of size 26 to mark the presence of each letter. While slightly less efficient than sets, it's easier to understand. Lastly, sorting the string and checking for all letters is another option, but it's inefficient with a time complexity of n log n, and is generally not recommended compared to hash-based approaches. Great job! Today, we reviewed the check if the sentence is Pangram problem, focusing on an efficient solution using a hash set. Remember the key concepts, such as leveraging hash sets for character uniqueness, and apply them in similar scenarios. Thanks for tuning in, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!